This video is about sinusoidal functions and their graphs. Sinusoidal functions are functions that are variations of the sine or cosine functions. So if you take a sine or a cosine function and you transform it, so you shift it up or down or stretch it or compress it, the resulting function would be a sinusoidal function. Here are the graphs of the original cosine and sine functions. The cosine is shown in blue, the sine is shown in yellow. Now, these two functions are periodic functions. So periodic functions have a few key properties, one of which being that they repeat. So that's why they get their name periodic, because the time it takes it to go through one full cycle before it repeats again is called a period. The sine and cosine functions happen to be periodic with period of 2 pi. So that means if I start here at y equals 0 and I trace out my cosine function, I get back to the beginning, so to speak, at 2 pi. So the same happens with sine. If I start here, my sine goes up and down and up, and then this is where I stop because that's where my sine function would repeat itself. It's at 2 pi. That is my x-coordinate here. So these functions also have what we call a midline. Now, a midline is the average between the highest peak and the lowest valley on your periodic function. And in the case of both sine and cosine, that midline happens to be at 0 because that's halfway between 1 and -1. This is a fine time to note that the range of both the sine and cosine functions is from -1 to 1. So that means the smallest output you'll ever have is a -1, and the biggest output you'll ever have is a +1. Now, the distance from the midline to the maximum is equal to the distance between the midline and the minimum, because that's how we found the midline. That distance, so this distance here, is known as the amplitude of our wave. Now, the sine and cosine function both have an amplitude of 1. Now, sine and cosine share nearly every property except for this one, in which the cosine function starts here at y equals 0 at its maximum, whereas the sine function starts here, right in the middle, at the midline, right at the origin. So our cosine kind of starts at the top and then falls down, and then our sine function starts here in the middle and works its way up to begin with. So if we were, however, to take our sine function and scoot it over by this distance, as I've shown with the purple arrows here, then our sine and our cosine functions would be overlapping. So if I shift my sine by pi over 2, because that's this distance here, then my sine and cosine functions would be overlapping. So that's really cool. So that means that when you're deciding whether to use sine or to use cosine to model your scenario, your problem that you'll be working on, it doesn't matter which one you choose as long as you have your horizontal shift correct. So the last thing I want to point out is the symmetry of the sine and cosine functions. So the cosine function has symmetry about the y-axis. That makes it an even function. So an even function means that if I change the sign of the input, it doesn't change the sign of my output. So cosine of -x equals cosine of x. The sine function, however, is an odd function. So odd functions have symmetry about the origin. So that means that sine of -x equals negative sine of x. So one way of thinking about this means that if we reflect it over the x-axis, it looks the same as if we had instead reflected over the y-axis. So visually and graphically, those two transformations do the same thing. I just want to take a quick look at how these operations affect our sine graphs, just to do a little quick review on transformations. So this here is the graph of 2 times sine of x. So it's a multiple out in front. This graph has been stretched vertically by a factor of 2. So we can see that our y-coordinate here has been moved from 1 to 2. That's no coincidence. It's because the factor out in front is a 2. So the first row in our little table here is going to be a vertical stretch by 2. So So the next graph we're going to look at is the sine of x plus 2. Now, the black one there is the original sine function. The green one is the one that has been shifted up by 2. So otherwise, these two graphs are identical. It's just that every single point on the green graph is 2 units higher than the corresponding point on the black graph. So our graph has been moved up by 2 because this 2 is positive. If it had said minus 2, our graph would have been moved down by 2. So this is a vertical shift by 2. And I just want to go ahead and throw that in our little table. This is the graph of sine of x plus 2. So once again, the purple one looks really similar to the black one. It's just that the purple one has been scooted over some. You might guess from the fact that we have a 2 up here in our formula that the horizontal shift that has taken place is by 2. It's kind of hard to tell because our axis here is measured in fractions of pi. But pi, remember, is this distance that I've just drawn in, is 3.14. So it's kind of close to 3. So if you think, okay, so maybe about 2/3 of that distance, and that happens to be exactly how far, our graph has been shifted to the left. So this was a horizontal shift left by 2. So go ahead and add that to the table here. Horizontal shift left by 2. And then our last graph for our table is the sine of 2 times x. So what that has done to our graph essentially is as if somebody has grabbed the ends and just kind of smushed it in together. It's been compressed horizontally. I like to think of it like an accordion. So this compression here, you can see, has made our red graph compared to a black graph. It covers twice as many waves or repetitions as it takes the regular sine graph to make the same, or to make a single repetition. So if we trace out our regular sine graph, we get through one period in 2 pi. However, our red graph here covers twice as much distance or twice as many repetitions in the same distance. So that it's got that doubled number of repetitions in the same amount of time. That's how this 2 affects that there. So this last one is a horizontal compression by 2. Now in a practical scenario, we're going to have more than one of these transformations happening at a time. So when that happens, we need to have a convention for what order to do them in to make sure everybody's getting the same answer. So this is kind of how we would write the general formula for our transformations. I've used f here in place of anything else because this is generalized for all functions, so whether it be sine or cosine or polynomial, whatever. This is how it's going to go. So I just went ahead and used f for that standard function notation. So if we have a transformed function, the first transformation we need to do is this b right here, because what we're going to do is plug in our x, and then we could distribute this b, and then we'd have to multiply our b times our x first. So that's the first transformation we have to do. So that b is on the inside of our function with our x, so that would be this horizontal compression. So that's what our b does. The next step we need to take care of is this h here. So this is what's been subtracted or added to x. And that would be from this example right here. So that's our horizontal shift. The next transformation we take care of is this a out in front. That comes third. And the a in front is like this first example we had. So that's our vertical stretch or compress. And that leaves our k over here for last. Going back to our table, our plus k here on the outside was our vertical shift, up or down. So this is kind of a general overview of your transformations. So now that we've seen how these different transformations kind of affect our graph independently, and we've talked about how to put them together, I think that it's really important to discuss how the different transformations affect the special properties of our periodic functions, because sinusoidal functions are all going to be periodic. They're going to have those same special properties, the amplitude, the midline, the period. Coming back to this first example, the graph of 2 times sine of x. This is our a out in front. So in general, we want to know, what does a times sine of x look like? So one thing that we can always count on is that we're going to have to multiply our y coordinates by this a. So that means that our amplitude is always going to go from 1 to whatever a is. So in the case for this specific example, our a was 2, and our amplitude then became 2. So if our a happened to be a fraction, like 1/2, for example, our graph would have gone down. It would have compressed vertically, and our new amplitude would have been 1/2. So it still would have been a. Therefore, whenever we have an a out in front, the amplitude of our new graph is going to be absolute value of a. So I say absolute value of a just because amplitude is a distance. Remember, it's the distance from the midline to the maximum, and it's also the distance from the midline to the minimum. But distance is always positive, regardless of whether we're above or below the midline. When we shift our graph up by 2, every single point has gone up by 2. So our midline kind of goes up with our graph. So our midline was here, and our new midline happens to be exactly 2 units higher. And that would have happened similarly if our graph had been shifted down, because our new midline would then become -2 if I had shifted it down by 2 instead. So whatever k is, in this case it was +2, but it could have been negative. So whatever k is the new midline. So the midline of your transformed graph is always going to be y equals k. So this here, sine of x plus 2, was a horizontal shift by 2. So the general formula here would be sine of x minus h, in which case h is always going to be a horizontal shift to the right. And then if the number that we plug it in happens to be negative, then we would go to the left. So that kind of makes it a little bit more intuitive with what happens to our graph if we use x minus h in our formula. So our horizontal shift is always going to be h. Now that's not necessarily a property of a periodic graph, just having a horizontal shift. But what is really cool about the horizontal shifts of a periodic graph is that if you shift the graph by its period, it overlaps with itself. So for example, here, our original sine graph has a period of 2 pi. So if I took the whole thing, all of this, and I shifted it over by 2 pi. So I took this point and moved it here, and then I took this point and moved it here, for example. Then my new graph would be the same, just over in a different spot. So it would overlap with itself. This property is called it's a phase shift. So if you shift a periodic graph by a multiple of the period, then the new graph that you get will be identical to the old one. Now, before we discuss directly how our period is affected by our transformations, I want to look at a few examples. So the first one I want to look at is just the graph of regular sine of x. We know that the period of sine of x is 2 pi. Now I want to go back and look at the graph of sine of 2x. So when we looked at this one before, we noticed that in the same time span, we doubled the number of repetitions that our sine wave was able to get in. So that's what happened in terms of time, kind of. But if we think about just the period of the new graph, although we multiplied our inside by 2, our period was cut in half. So our period now is 1/2 of 2 pi, which is just pi. So shown in green here is the graph of sine of 4x. So I just want to trace that out and see what the period is. So the period of this green graph here is pi over 2. So once again, the period of our original sine function was 2 pi. So pi over 2 is 1/4 of 2 pi. So that means I can fit 4 repetitions into 2 pi. Now I want to look at what happens when our b, the number we're multiplying our x by on the inside, is a fraction. So in this case, it's 1/2. So our new period here is 4 pi. So that means now it's taking twice as long for our graph to get in a full period, a full cycle, because we're moving at half the speed, is the way I like to think about it. So our period here is 4 pi. Our period is twice as long because we've got this 1/2 in here. So in general, the way it's going to work is whatever our b is in here times our period, whatever that is going to be 2 pi. So right here we've got 1 and 2 pi. Their product is 2 pi. For the second one, we've got 2 and pi. The product of 2 and pi is 2 pi. The next one, 4 and pi over 2. If you take 4 pi over 2, that reduces to 2 pi. And then, once again, when we multiply, we end up with 4 pi over 2, and that's 2 pi. So that means our period times b is always going to be 2 pi. So in order for this to always be true, so we don't have any sign errors, I'm going to throw the absolute value here on our b, because our b could be negative, but our period, since that's a measurement, is always going to be positive, and positive 2 pi is always going to be positive, so we need a way to make sure b is positive. So that's why I put in the absolute values. So the period of any general sine function that's got a factor of b here on the inside with x is going to be 2 pi over absolute value of b. So if we go back to this little diagram we've got going, I can go ahead and fill in what happens. So this b affects our period. Our vertical shift affected our midline, and then our vertical stretch affected our amplitude. And then the horizontal shift didn't affect a special property of our graph, but it does have a special property called the phase shift. So remember, that was the property where if we shift our graph by a multiple of the period, we get the same graph. Now I want to move on to an example. So this example says, let y equal 2 sine of 2x minus pi in quantity plus 2. Find the amplitude, period, midline, and horizontal shift of this function. So remember, our amplitude was a in absolute value. Our period is 2 pi over the absolute value of b. Our midline is y equals k. And our horizontal shift is h. So these all hold true if our transformation, or our transformed function here, is written in the proper form that we had it. So notice that in our problem here, we have 2x minus pi, and in our proper form, our b was factored out. So the way that it's written for us would be as if this b had been distributed. So we need to factor out this 2 here. So when we factor out a 2, we need to take a factor out of this term and this term. So we end up with pi over 2 right here. And our h is the right sign because we've got a minus here, and that's how it is in our proper form as well. So our amplitude is the absolute value of 2, which is just 2. Our period is 2 pi over the absolute value of 2, so that's a positive 2 over positive 2. Those cancel, and we're left with pi there, not 2. Our midline is simply y equals k. Here in our example, our k is positive 2, so our midline is at y equals 2. And lastly, our horizontal shift is h, so we can just go ahead and pull this h out, and our h is pi over 2. So that's a shift to the right by pi over 2. So here we've basically taken an expression, we've broken it down, and determined all of these properties of our graph. So theoretically, if we're given a graph, we could identify these properties and then construct the formula. So that's what we're going to do in our next example here, example 2. It says, find a formula for the sinusoidal function to the right. So that's that graph up in the right corner. So before I even think about constructing a formula, I'm going to go ahead and just identify the properties of this periodic function that we've got shown here. So right off the bat, I can see that my graph goes from 10 to negative 10. Hey, that means my midline is right on x equals 0. That's pretty convenient. Because we know if our midline is at 0, then our k equals 0. I can also see right off the bat that since my k is 0, my midline is 0, my highest point is at 10. So that means my amplitude is 10. So that means absolute value of a equals 10. So I need to decide if my a is actually positive or negative. So before I can do that, I need to decide if I'm using my sine function or my cosine function. So going back to my original sine and cosine functions, I said that one of the key determinants we were going to be using to decide which one to use would be where our graph started. So remember, our sine function started at the origin here, kind of in the middle of the graph, whereas our cosine function started at the maximum. So anytime we're looking at a graph that starts at the maximum or the minimum, we're probably going to want either cosine or reflected cosine. If it starts here at the origin, we're probably going to want it to be either a sine or a reflected sine. So for this example, the graph that we're looking at starts at the origin. So we're going to want to use a sine graph, because that'll make it just a little bit easier on us. And then we can say, hey, this graph has been reflected. So when I talk about my reflection, I can either do that using my A, or I can include it later with my B. However, I'm just going to go ahead and do it with my A so I can get it done and over with. So I'm going to call my A here -10. So the 10 is for the vertical stretch that we see, and then the negative is because I'm saying that this graph has been reflected over the x-axis. So since we chose the sine function, it's pretty convenient because this graph starts right here at the middle of the graph, right on the origin. So that means that since we're using sine, we don't have to worry about a horizontal shift at all. So we can go ahead and just say that our h is 0. And then the last thing we have to worry about is our b. So in order to find our b, we can look at our graph and determine what the period is. So I'm just going to start at the beginning of the graph and trace it out, and I see, hey, I start over once, and then I can get through a whole complete cycle before I get to 4. So if 2 full cycles happen over a span of 4 units, then 1 full cycle happens over a span of 2 units. Therefore, my period is 2. So I know that 2 equals 2 pi over the absolute value of b. I then get that b equals the absolute value of b equals pi. That means my b can either be positive or negative pi. Well, remember, for our horizontal stretch and compression, a negative means that we've reflected across the y-axis. So we've already determined that the reflection we're seeing, we're going to attribute it to our A here and call our A negative. So that means our B is not causing a reflection in our graph, so we are going to call our B positive. However, if we had gone back to this previous step and elected to call our A positive 10, then we would choose negative pi. However, that's not the case. Our A is negative. That accounts for our reflection, so now we're going to choose positive pi for our B. So now I've determined my function, my A, my B, my H, my K, and now I can write the full formula for this function that's pictured here at the right. So we've got -10 times sine of pi times x minus 0 plus 0 is the function for the graph. So that simplifies to 10 times sine of pi x. This being our final answer. So a perfectly acceptable answer, alternative to this would be 10 times sine of negative pi times x. These two things are equivalent because the sine function is odd. So that means if we change the sign of our input, here it changes the sign of our output. For example 3, we're asked to find a formula for the sinusoidal function pictured to the right. Once again, this graph is a little different from the other one. So the other one, it was really clear whether or not we should use sine or cosine, because here our starting point lined up kind of perfectly with the starting point for our sine function. In this example, however, we see that our starting point, if we call our y-axis our starting point, is off. It's not at the maximum and it's not in the middle. It's somewhere in between. So it would make sense then to either use the sine or the cosine function. So the way I'm going to determine it is just by choosing whichever one seems to have a point that is more easily identifiable. So right off the bat, I can see that the peak right here has an x-coordinate of 1. So if I start at that easily identifiable peak there and trace it out until I hit a period, that looks just like my cosine function, except it's been shifted over to the right by 1. So I'm just going to go ahead and use cosine. Now, when I determined to use cosine, I also determined there that the shift h that I was using was a shift to the right by 1. So I'm going to call my h 1. So we can kind of look at our graph and see that our max here is at 3, and then our minimum here appears to be at -1. So then halfway between those would be our midline, and that is at +1. So if our midline is at +1, then our k must be +1. And now that we've determined our amplitude, or our midline, we can determine our amplitude rather easily. So our amplitude is just going to be the difference between our maximum and our midline. So the difference between 3 and 1 there is 2. So the absolute value of A equals 2. So this looks like a right side up cosine. So that's what I've based my h on, and that's what I'm kind of using as a model. So that means my A is going to be positive then, because there's no reflection going on. So I can get rid of those absolute values and just have that A equals 2. Now the last part we need to find for our overall function is our B. Now in order to find our B, we need to first determine our period. So I kind of said that my function, quote unquote, started here at 1. So then we have to see where it gets back to the beginning. So that was over here. And that appears to be at x equals 11. So if our graph starts at 1 and then starts over at 11, then our period here was 10. And we know that our period equals 2 pi over absolute value of b. And we get that b equals pi over 5. And that's positive because the b wouldn't even cause a reflection in the cosine. So if you just keep your reflections going with your A, you can just always call B positive, so that'll work all the time for sine or cosine. That's why I said I usually just do it that way, because it's easier. So anytime you've got a reflection, just call your A negative, and then don't worry about what's going on with your B. Just make your B positive. So now I've got my B, my H, my A, and my K, and I can plug all of those in to find a formula for this function. My A is 2, and I chose cosine. My B is pi over 5. My H was 1. And my K was positive 1. So this is my final answer. Now, I would encourage you to try this problem again, except this time using a sine function. So if I were to use a sine function to do this problem, I would go ahead and identify my midline, and then decide kind of where I want my sine to start from. So just so I don't have to worry about a reflection, I'm going to choose this point right here, which looks like it's at -1.5. So I chose that point because my regular sine function kind of starts at the origin and goes up. So I would go ahead and pause and try to work this one out, and then I'll have the solution for you on the next screen. So this is the solution for the sine version of the problem. So notice the only thing that changed here was my h, my shift. That was dependent on the fact that I chose sine for this one opposed to cosine in the solution. Because I was making up my answer from the same graph, my amplitude was obviously going to be the same. My b, which determines my period, had to be the same because both of these equations, this sine version and the cosine version that I had up a few minutes ago, those both represent the same graph. So that means my midline is also going to be the same. So my A, my B, and my K are all going to be the same. The only thing that changes, depending on what I use here, is my H. So that simplifies to a final answer of 2 times sine of pi over 5 times x plus 1.5 into quantity and quantity plus 1.